Mechanical oscillations. Last semester, when we introduced the subject of AP Physics, we talked about motion. I specifically said that AP Physics C Mechanics is concerned with Newtonian mechanics. And we did define Newtonian mechanics as the study of systems in motion and the underlying causes or the forces that brings about this motion. Now, if you reflect back carefully, you will see that motion can be categorized basically into three. Now you have linear motion, which basically is due to external forces impressed on a given system, and the motion can be explained from Newton's three laws of motion. You have what we call rotation, in which embodied is circular motion as well. Now, rotation is basically due to external torques acting on rigid bodies, and we know here that the summation of forces acting on that system is equal to what? MA, and we know here that the summation of torque is equal to I alpha. Now, and lastly, that the last type of motion that we will discuss in this class will be oscillations or mechanical oscillations, to be more specific. Now, oscillations are due to restoring forces. Oscillations are due to restoring forces. Now, this particular type of forces, a restoring force is a resultant force. Keep that in mind. Which is a resultant force, so the summation of F will be equal to negative K delta R, where delta R, as usual, is the displacement of the object. Where delta R is the displacement of the object. Now, these are the different types of motion that essentially you will study in AP Physics Mechanics. We've done the first two, and now let's knock out the last. But really, just the name oscillation, what does that mean? A system that is oscillating undergoes what we call repeated motion. In other words, the motion of the system is repeated about an equilibrium position. About an equilibrium position. Naturally, every system wants to be in equilibrium. Let me say that again. Naturally, every system wants to be in equilibrium. Now, for oscillating systems, they do what? Oscillate about an equilibrium position. So the very first important point I need for you to take down is that every mechanical oscillating system possesses an equilibrium position. Every mechanically oscillating system possesses an equilibrium position. What really is an equilibrium position? An equilibrium position is the position in which the system is undisturbed. Let me say that again. It is the position in which the system is undisturbed. An undisturbed system is one in which there are no net external forces acting on the system. Let me say that again. An undisturbed system is one in which there is no net external force acting on the system. This means that the system is in equilibrium. This implies that the system is in translational equilibrium, to be more exact. The next point I want to make is this. Every oscillating system has a period and a frequency. Every oscillating system has a period and a frequency. The period T is the time required to make one complete oscillation. Is the time required to make one complete oscillation, and is defined as the total time taken divided by the total number of oscillations, measured in seconds. measured in seconds. Now, the frequency F is the number of oscillations made per second. The number of oscillations made per second, which means that the frequency F is equal to the total number of oscillations divided by the total time taken. If you compare these two equations, what we can see is that T is equal to 1 over F. In other words, the period is a reciprocal of what? The frequency. The period is the reciprocal of the frequency. The third important thing you need to note about oscillating systems is that every oscillating system, let me put it this way, when an oscillating system is displaced from its equilibrium position, a restoring force is generated that tries to restore equilibrium. Let me say that again. When an oscillating system, it doesn't matter which, is displaced from equilibrium position, a restoring force is generated that tries to bring back the system to equilibrium. Do you understand that? Write that statement down, please. When a mechanical oscillating system is displaced from its equilibrium position, a restoring force is generated that tries to bring back the system to equilibrium. Recall, listen to my statement. The restoring force only exists if there is what? Who can finish the statement? If there is displacement. If there is displacement. Good. Now, understand that there's a big correlation or relationship between the restoring force and the displacement. Now, write this in red and bold. The restoring force is proportional to the displacement from the equilibrium position. Are you there? The restoring force is proportional to the displacement from the equilibrium position and always directed towards the equilibrium position. And always directed towards the equilibrium position. And always directed towards the equilibrium position. What basically I'm saying is that the restoring force, F restoring, is proportional to negative delta R. Why is it negative? It's negative because the displacement is away from equilibrium position. The restoring force is always directed towards the equilibrium position, which means that the two vectors are always oppositely directed. Do you understand that? Are oppositely directed. Hence, we can see that the restoring force is equal to negative K X. Let me use scalar so it makes the mathematics easy. The restoring force is equal to negative Kx. So if you draw a graph of our restoring force F against the displacement X, it's actually going to be negative like that. That will be how the graph will look like. Now, this constant K is always positive. It's a positive constant. It's always positive. Before I proceed, I have mentioned the following important factors. Let's review them. Throughout this chapter, which is pretty short, you will use these 4 points in analyzing the systems. 1. Every mechanical oscillating system has an equilibrium position. 2. Every mechanical oscillating system has a restoring force that always tries to restore the system back to equilibrium position. Now, just to let you know, a restoring force is a resultant force, just like the centripetal force. which means that a restoring force really cannot be represented in a free body diagram because it is what? A restoring force. I'll explain that a little bit further. Every oscillating system has a period and a frequency. Why? Because oscillation is repeated what? Motion. And if for those of you who have mathematical minds, and if it's oscillating, it means that the function that defines a mechanical oscillating system is a periodic what? Function. And if it is a periodic function, the most common periodic functions involves what? Sines and cosines. Do you understand that? Involves sines and cosines. Now I'm leading you somewhere. Pay attention. Lastly, and very important, every mechanical oscillating system must be elastic and must possess mass or inertia. Write that down. Every mechanical oscillating system must be elastic, must possess mass or inertia. Now, why is this important? A system cannot oscillate without interchanging potential energy and what? And kinetic energy. For you to have kinetic energy, you need mass or inertia. For you to have potential energy, you have to be what? Elastic. So these are the properties that must be possessed by a system in order for the system to perform mechanical oscillation. Now, I will say here that when analyzing mechanical oscillations, there are two important models that you could use. You could either use the constant mechanical energy transfer model, or you can use what we call the restoring interaction model. Some people will prefer to say elastic restoring interaction model. Now, these models simplifies the analysis of mechanical oscillating system. Now, I'm going to summarize these two models, and then we will analyze every system parallel with the two models so you could see the differences and choose which one you want to use. The central tenet, listen fellas, please listen. The central tenet of the elastic restoring interaction model is the restoring force. The restoring force. Now, according to this model, when a system is displaced from its equilibrium position, a restoring force is generated that brings back the system to equilibrium. Are you with me? When a system is displaced from its equilibrium position, a restoring force is generated that brings back the system to equilibrium. Now, quantitatively, the magnitude of this restoring force is proportional to the displacement of the object from equilibrium position. Think about a spring. The more you extend the spring, the more it feels what? Stiffer. When you let go, what happens? It springs back faster. You understand that, right? Let's put it mathematically, which you will be amazed how simple it looks. F is equal to negative kx. And recall that this F is a restoring force, which means that this implies that MA is equal to negative kx. Therefore, A is equal to negative k over m multiplied by what? X. Therefore, this gives you the acceleration of a particle undergoing simple harmonic motion. Now, this constant is always positive. This constant is always positive, and because of that, let's represent it by omega squared. This implies that omega squared is equal to k over m. This holds true for all motion that you will encounter. In other words, k is equal to m omega squared. Hence, we can see that this means that the restoring force is equal to negative m omega square x. This gives us the formula for the restoring force. If you have not recognized this, we already analyzed this problem the second week of classroom. The second week of class, we did solve this problem. This is the first difficult problem you ever made. And we are going to do it again anyway, just for repetition. In that problem, I gave you the expression of acceleration to be equal to this, and I did ask you to solve for Vx as a function of what? Time. And when we did that problem, we were done with mechanical oscillations. So technically, we could kiss goodbye to this and say go home. We are done with the topic. But anyway, let's review. Now, look up everybody. Look up, please. Look up, look up, look up. We know that that A is equal to negative omega square x, where omega squared is equal to k over m. Any system whose acceleration is given by this expression is a simple harmonic oscillator. It's a simple harmonic oscillator. Let me say that again. Any system whose acceleration is given by that expression is a simple harmonic oscillator. And it exhibits mechanical oscillation, and specifically, that type of mechanical oscillation is called simple harmonic motion. So if you are asked to define simple harmonic motion, you are free to say that an object undergoes simple harmonic motion if its acceleration is given by that. Comprende? Now the second differential equation that governs this expression, A is equal to what? d2x all divided by dt squared, which implies that d2x over dt squared is equal to negative omega square x. In other words, d2x divided by dt squared plus omega square x is equal to 0. This is a second order differential equation, and this equation is what we call the simple harmonic oscillator equation. Write that down, please. Simple harmonic oscillator equation. Simple harmonic oscillator equation. To solve this equation, I can show you several methods to do this equation. How many of you here have learned how to solve differential equations? Put up your hand, let me see. I didn't say second order, I said differential equations. Can you solve this equation now? You can always reduce a second order differential equation to a first order differential equation. Alex, you should know how to do this. Come on.
Hold on, give me like 3 minutes.
Now, look up, please. Let me show you. Let me show you. You can either do it using brute force, or you could be a little clever. Remember that this expression A equal to negative omega squared x is the same as d2x dt squared plus omega squared x equal to 0. Now, to solve this differential equation, you need to write down its particular solution. I know you haven't heard that, so I'm not even going to go there, though it's much more fun. Now, let's come back here. You know that A is equal to what? dv over dt, which is going to be dv over dx dot dx over dt. This is v dv dx. Therefore, this implies that v dv dx is equal to negative omega square x, which can be simplified to v dv equal to negative omega square x dx. Now, we have separated the variables. If we take the integrals of both sides, you have the integral from v naught to v of v dv equal to negative omega squared, the integral of x dx from what? From x naught to x. Now, I'm going to assume that the initial velocity here, initially the system is at rest. That would mean, can we go to the next slide? This would give us v squared over 2 from 0 to v equal to negative omega squared x squared over 2 from x naught to x. This, therefore, will be equal to omega squared, this is over 2, x naught squared minus x squared. Now the 2's can cancel. This implies that v squared is equal to omega squared bracket x naught, x naught squared minus x squared. This expression gives you the equation for the speed of the particle. Gives you the equation for the speed of the particle. That means when you look at this expression, it is the equation of what? It is the equation of, no, think about it. Look at, in terms of mass, where have you seen an equation that looks like this? They're usually done in conic sections. And this expression represents, okay, let me analyze this. You haven't recognized this. Let's analyze this now. Please watch, please. Watch. All right. When at equilibrium position, please listen carefully. At equilibrium position, x is equal to 0. And if x is equal to 0, this means that v squared will be equal to omega squared x naught squared. In other words, this implies that v is equal to plus or minus omega x naught. This is v max. The velocity is maximum at equilibrium position. That is the conclusion. The velocity is maximum at equilibrium position. Next slide. At amplitude x is equal to x naught. At amplitude, what is the amplitude? The amplitude basically is the maximum displacement from equilibrium position, the maximum displacement from equilibrium position. At amplitude, this implies that v squared is equal to omega squared x naught squared minus x naught squared, which is equal to 0. So we could conclude that the velocity is 0. Some people would prefer to say minimum at amplitude. It's 0 at amplitude. Are we together? What about acceleration? What about acceleration? What about acceleration? A is equal to negative omega square x. This implies that when x is equal to 0, a is equal to what? 0. So the acceleration is 0 at equilibrium position. And that makes sense because at equilibrium position, the net force is also what? 0. Do you understand that? The net force is also 0. Similarly, when x is equal to x naught, a is maximum, which is equal to negative omega square x naught. This means that the acceleration is maximum at amplitude. This means that the acceleration is maximum at amplitude. And if that is true, then we can draw this graph. This is x. You have here x naught, here negative x naught. This is v in meters per seconds, and this is 0. And the graph will look like that. For acceleration, this is x, and this is a. The graph will be like that. You see graphs like this in the multiple choice section quite a lot. Now, keep in mind that one, f is equal to negative m omega square x. 2, a is equal to negative omega square x. 3, v squared is equal to omega squared x naught squared minus x squared. This means that v is equal to omega, the square root of x naught squared minus x squared. In other words, dx dt is equal to omega, the square root of x naught squared minus x squared. If you separate the variables, you will have dx all divided by the square root of x naught squared minus x squared equal to omega dt. You can now integrate from x naught to x. You can integrate from 0 to t. Now, this is an intricate inverse trig integral. You can replace this as so how do we differentiate this expression? We can use a trigonometric substitution, right? We did this before, not once but twice. Now look up, fellas. Look up. If we, on the one hand, choose to say that let x be equal to x naught sine omega t or sine theta, doesn't matter. This would imply that x naught squared minus x squared will be equal to x naught squared minus x naught squared sine squared theta, which is just going to be x naught squared cosine squared theta. We have used the trigonometric identity. Sine squared theta plus cosine squared theta is equal to 1. So if we substitute, remember that dx will be equal to x naught. What is the derivative of sine? Cosine theta d theta. So if we substitute all of this back into that expression, you would have the integral of x naught cosine theta d theta divided by the square root of x naught squared cosine squared theta, all of this equal to omega t. And it pretty much simplifies to the integral of d theta equal to omega t. But what are the limits? We know that x is equal to x naught sine theta. So we can see that when x is equal to 0, when x is equal to 0, theta is equal to what? 0. When x is equal to x, theta is just the sine inverse of x over x naught. So we are starting here from 0 to sine inverse of x over x naught. This would imply that the sine inverse of x over x naught is equal to omega t, which implies that x is equal to x naught sine omega t, and that is the expression for x. Now this is clear if you understand the basic rules of integration here, and if you've forgotten, it therefore tells you that you need to go back and review. Now what do you see? This expression is true if we would have said, for example, that if this was not 0, if x naught didn't start from the origin, what could have happened to the lower limit if it didn't start from the origin? For simplicity, yes please. So you discover that this expression depends on the value of the lower limit. So if you draw a graph of x against t, it is a sine function just like we predicted. We predicted that the motion of a mechanical oscillating system is periodic and therefore will be defined by a periodic function, either sine or cosine. And finally, our answer is the same, true. So if we draw the graph, it will be a sine function, beautiful curly function, like that. Any questions? Keep in mind that we have said that omega squared is equal to k over m. In circular motion, omega is equal to 2 pi over what? T, which is equal to 2 pi f. Keep this in mind, this is true all the time. And if that is true all the time, this implies that 2 pi over t all squared is equal to k over m, which implies that t is equal to 2 pi the square root of m over k, and that is a period of oscillation of the system, and that is a period of oscillation of the system. So we could see that. Let me give you this example here. It's from the book. The equation of a mechanical oscillating system is given by. Can you guys determine the period and the frequency of this system? Generally, we know that d2x dt squared plus omega squared x is equal to what? 0. Comparing these two, omega squared is equal to 4 pi squared. This implies that 4 pi squared over t is equal to 4 pi squared over 1, which means that t is 1 second. And if t is 1 second, f is equal to 1 over t. This implies that f is equal to what? 1 hertz. Is it clear to everybody? Is that clear? This is a quick multiple choice questions that you should not miss. Now look up please. Generally, you're writing please. Generally, a system undergoing simple harmonic motion. Generally, the position of a system undergoing simple harmonic motion is given by. Generally, the position of a system undergoing simple harmonic motion is given by x equal to x naught cosine omega t plus phi cosine omega t plus phi, where phi is known as the phase constant, or phase angle. The value of phi is given by the initial conditions. The value of phi is given by the initial conditions. For example, when I talk about the initial conditions, I mean the value of x and v at t equal to what? 0. Okay? The value of x and v at t equal to 0. For example, if x is equal to 0 at t equal to 0, this implies that 0 will be equal to x naught cosine of what? Phi. And this implies that phi will be equal to pi over 2. Phi will be equal to pi over 2. Therefore, in this case, x will be equal to x naught cosine of omega t plus pi over 2, which is equivalent to what? X naught sine omega t. Using complementary angle identities, cosine omega t plus pi over 2 is just sine omega t. I could prove that to you if you want. Yes, please. Now, it's essential at this point that you go home and review your trig. This is the same, review your trigonometry. We'll use it this semester, we'll use it in E&M as well as in MEC. So note the following, please note the following. Every system performing simple harmonic motion, you're writing please, you're writing. Every system performing simple harmonic motion possess the following properties. Every system performing simple harmonic motion possess the following properties. One, there must be a restoring force, F given by negative kx, which is the same as negative m omega square x. 2, the position, velocity, and acceleration of the system are all sinusoidal functions of time. X is equal to x naught cosine omega t plus phi. V will be equal to what? Negative x naught omega sine omega t plus phi, and acceleration A will be equal to negative x naught omega squared cosine omega t plus phi, if you do your calculus correctly. The third point is the period and frequency of oscillation. Listen carefully, please. This is really important. The period and frequency of oscillation is entirely independent of the amplitude of oscillation. Is entirely independent of the amplitude of oscillation. Is entirely independent of the amplitude of oscillation. And the last important property, this is actually on page 1013 in your textbook. The system must be elastic and must possess inertia. The system must be elastic and must possess inertia. The system must be elastic and must possess inertia. In your next exam, there will be a question on this.
Good morning, faculty and student body. At this time, please read the daily announcements. Teachers, please check dress code. Thank you. Good.
Look up, fellas. Look up. We are going to talk about the constant mechanical energy transfer model now. Okay? So, and I'm going to review. We've done this before, so this is just basically a review. Write this down, everybody. Write this down. It is obvious, but some of you may not have seen this. The restoring force is a function of position only. Alex, what does that imply? Now, what does that mean in terms of energy? If the force is a function of position only, it means that the system is conservative. I'll give you a point for that. Now, it means the system is conservative. That is really so important. Now, write that down, please. The restoring force is a function of position only, implying that the system is conservative. What does it mean for a system to be conservative? Any ideas? Yes, Jacob? Great. The mechanical energy remains constant with time. Add that there, please. It means that the mechanical energy remains constant with time. Again, what does that mean? There is one more point left that is very important. that is only true for conservative systems. The work done around a closed path must be 0. The total work done around a closed path has to be 0. Now we have, take note that for conservative system, f sub x is equal to negative du over dx, where u is the potential energy. I prefer to call it the potential energy function. This implies that delta u is equal to the integral, negative the integral of fx dx from 0 to x. For simple harmonic motion, this becomes the integral from 0 to x negative kx dx, which is just the integral from 0 to x kx dx. Hence, you would have the potential energy u x equal to 1/2 kx squared. You saw this before, right? You've seen this before. This can be re-expressed. We know that k is equal to what? M omega squared. That would mean that ux will be equal to 1/2 m omega squared x squared. That is another way to express the potential energy. And this is the potential energy of a particle undergoing what? Simple harmonic motion. Look up, please. If you recall a while ago, we did show that v squared is equal to omega squared x naught squared x squared. Therefore, the kinetic energy will be equal to 1/2 mv squared, which will be equal to 1/2 m omega squared x naught squared minus, well, minus x squared. This is the kinetic energy of a particle undergoing simple harmonic motion. The total energy, E total, is equal to Ke plus Pe, which will be equal to Ke is 1/2 m omega squared x naught squared minus 1/2 m omega squared x squared plus 1/2 m omega squared x squared. This takes care of each other and implies that the total energy of a particle undergoing simple harmonic motion is 1/2 m omega squared x naught squared. Now the thing that I want you to take home here is, if you look at that expression, the total energy is constant. The total energy is constant.